Christine. I'm from the USA team, and today I'm going to present the problem long shot. So let's review the problem first. Suppose we have a very good archer, and he can shoot the arrow vertically up at a maximum power, and he can take wind speed and Coriolis force into account. What would be the maximum deviation from the target given all the uncontrollable factors? So first, I want to do some numerical analysis of the problem, so I have to first make some general assumptions. So I assume that the air density is 1.125, which would be changed later. And then I said that suppose the projectile cross-section is a circle, just that it's easier to calculate the sectional area using pi r squared. Then I said that the sideway air resistance is negligible because it's on the magnitude of 10 to the negative 3, which is very small compared to the other forces. And then I said that the wind direction is in phi, which, well, I use spherical coordinates here, so basically on Earth it would be going from west to east, like only in that direction. And then I said that the wind speed is 3 meters per second, which is pretty strong usually. Then I assume something about the arrow. Here's the mass, it's diameter, and its drag coefficient, 0.3. And I said that its initial velocity is 120 meters per second, which is the maximum power, and it spins at 1200 rounds per minute. So the first factor I considered is air resistance, which is also called drag, and here is the drag equation. It's proportional, so the force is proportional to v squared. And from that equation plus the gravitational force, I derived the ascending and descending velocity of the arrow. And with that, I calculated that the time of flight with drag would be 22.1 seconds, while the time of flight without drag would be 24.4 seconds. And counting that timing. Using the wind velocity times the delta t, I get a deviation of about 0.9 meters. Next, I consider if air density changes, because it's very easy for air density to vary. It has dependence on the pressure of the atmosphere, P, and the temperature of the atmosphere with the relationship rho equals P over RT. So first, I consider the ascending time. According to the differential equation that I had, the ascending time would be proportional to arc tangent V naught. Well, you can see the equation, it's too long for me to read. And because the arc tangent factor doesn't change much when V naught is big enough, say at 100 meters per second, it is also proportional to 1 over square root rho, while at large t, the descending time doesn't really depend on air density. So according to that, I get the conclusion that the displacement from the target increases as air density increases due to drag force. The next thing I consider is Magnus effect. So I have made to demonstrate it with me. So suppose here's the arrow, and here's spinning in that direction, and I am wind coming in this direction. So the velocity on this side would be bigger, and due to Bernoulli effect, the pressure on this side would be smaller than the pressure on that side. So you actually move this way, yeah. Sorry. So yeah, due to the pressure difference, the arrow will not be more moving forward away from the usual trajectory. And here is the equation to calculate the magnitude of Magnus effect, which would be about 0.656 meters. Then I also considered the fact of turbulence. So here we consider Reynolds number, which is the number so if Reynolds number is about 10 to the 3 to 10 to the 4th magnitude, it would usually start a turbulence. And as we can see from the calculation, I think the result would be about 2 times 10 to the 4th, which would be enough to start a turbulence. And people use Navier-Stokes equations to calculate turbulence. Unfortunately, these equations are never solved by anyone, so I don't know how to solve them either. So I guess I can't give a numerical evaluation of that. However, turbulence is usually offset by deflection, like the end part of the arrow that I have. So an arrow looks something like this with some flashing at the end, and this would help to stabilize the arrow. And so, for example, if there's some turbulence, it would simply spin faster so that it can stay on its course. However, that would somehow affect the Magnus effect. Yeah, as I said, I cannot really give a magnitude-wise calculation of that. Here I also just calculated Coriolis force just for comparison. And yeah, these are the comparison numbers. Apparently the deviation due to drag and Magnus effect in this case is actually bigger than Coriolis effect. So next I will calculate bullet just because it's problem as well. And I made these assumptions from that kind of bullet, which is commonly used in American Army. So the deviation due to drag would be about 42 meters, and deviation due to Magnus effect would be about 20 meters. Another special thing about bullet is that the velocity of bullet would be enough for it to enter the transonic region, which is about 0.8 to 1.2 Mach number, which is also about 300 meters to 400 meters, 300 meters per second to 400 meters per second. During this part, one thing would change, that is the center of pressure would shift forward due to deceleration. So usually we have a bullet with its center of mass in front of the center of pressure, and it's moving in this direction. So this is the stable version. And during the transonic region, the center of pressure would sometimes shift in front of the center of mass, which would cause the bullet to behave in an irregular way. This factor is also very hard to calculate, but it sometimes happens during the transonic region if the shift is enough to push the center of pressure in front of the center of mass. Okay, I also tried to do some experiments. Unfortunately, I could not get very conclusive results of that due to several reasons. The first reason is that, well, I'm not a very professional archer. Actually, I'm not an archer, so I cannot shoot the arrow at 120 meters per second. Instead, I have an initial velocity of 30 meters per second, which reduces the Magnus effect, the Coriolis effect, and the drag force effect by a lot, by about, I think, 1/4, actually 1/6 of the drag force. Yeah, and also I cannot shoot it up vertically because no one would allow me to do that. So I have to shoot it at an angle, and the total time of flight is also decreased by much. And then I also have a lot of difficulty in accurately measuring the deviation because I have to shoot the arrow on a very hilly place, and it's just very hard to see how much deviation it has. And I think the deviation I could observe are mainly caused by wind and not by the other factors that I have mentioned. So yeah, since I have some extra time, I will talk about, so gyroscopic drift can also influence normal bullet trajectory, but in this case, since we're shooting up vertically and there's no angle between between the direction of the velocity and the rotational axis, so this has no effect on vertically shot bullets. And another thing is that I used drag model to calculate the drag coefficient of the bullet, just because it's more accurate. And yeah, that's some citation I used, and that's the end of my precious presentation. Thank you.
So clarification questions from the opponent.
Okay, first, I will ask the reporters some questions. The first, in the serial analysis, except the air gap and Coriolis force, did you consider any other parameters?
What do you mean? I think all the factors that I talked about are other than wind and Coriolis effects. Like Magnus effect is not wind or Coriolis. Gyroscopic effect, yeah, any of these. Drag is not really wind, and Magnus effect is solid region and turbulence are.
Okay. And next, did you consider the difference on the Coriolis force between the different latitude in the Earth?
Oh yes. Yeah. Another assumption I made in this, I think I forgot to put it in the PowerPoint, is that it's x theta equals 45 degrees. So I only consider Coriolis force at this point, but yes, Coriolis force does change with latitude, and I think that's very easily calculable. You just plug in a different theta number and you would get a different result.
Could you turn to page 11?
11?
Why would you consider the air temperature to be 50 degrees centigrade?
That's just because I gathered the data. Like I found the data online, and they gave me this data. Actually, I have other data. So as temperature decreases, mu tends to decrease as well. I think at 20 degrees, I think it's 1.7 times 10 to the negative 5. So it doesn't really change by much, but.
And then there is the first.
The turbulence and Coriolis force is also very important. And interestingly, consideration and some class about experiment. Okay, and the first, her report has some the strengths. The first is has a very nice setup and explain the physical principle behind the experiment. And the key point is she considered the turbulence and studied the importance of the other main parameters. She is a well-performed experiment and compared between the theory and experiment. But also have some weakness. The first is she not narrowed the temperature. She not give the optimization and lack of the calculation process. This is the key problem in this long shoot. And the experimental data doesn't fit the theories very well, and when the initial velocity is very high. So, and the last is the didn't compare between the theory and experiment. The other questions is okay, that's all.
That's it?
Yeah, we can
start the discussion.
Okay, do you want me to address the weaknesses you pointed out first? Okay, so first you said that I didn't measure temperature in my experiment. Actually, there's a lot of other factors in the experiment. I didn't measure them because I don't have very valid data, as I explained previously in my presentation why my data doesn't work very well because of all those factors like that limitate the deviation from the target. The temperature was about 0 degrees Celsius. I shot an angle of 20 degrees. Those are the two most important factors. The second one, you mentioned optimization. I'm not sure, and I want you to later clarify what kind of optimization you mean, because in this, it's given that, well, I can shoot basically at whatever reasonable velocity I want, and the angle is up vertically, so those two major factors are already determined. As to the uncontrollable factor, I can't really optimize it because I can't really control it. Third, you mentioned calculation process. I'm not sure which exact calculation process you want me to demonstrate. I can do the math here on board if you want. Fourth, the experiment. The experiment and theory. Well, as I said, my experiment data isn't really that accurate, or actually it doesn't I can't really accurately measure the deviation, so yeah, I didn't really try to correlate them.
Okay, And another parameters is if the object is an arrow. So this is height and this is tail. So I think you didn't consider the mass distribution. Yes, the mass distribution is also the big difference between the arrow and the bullet. So this is the arrow, and if the height is higher than the tail, so it will produce different direction of torque. So if the head is higher than the tail, it produces inward torque. So this inward torque could influence the deviation of the displacement.
Could you clarify what torque you are talking about? Like
the torque is the mass of torque. The mass.
The torque produced by what force?
The gravity torque. The torque of the gravity.
It doesn't really rotate around because when an arrow is shot out, it's very stabilized. It doesn't rotate around itself.
So this cannot rotate in this surface. It can rotate it in this.
Could you?
In this surface.
Sorry, I'm not sure what you mean. Suppose this is an arrow. What do you mean by that?
So for example, this is the height and the tail. This is the tail, and if the head is higher than the tail, so it will have a bigger torque than the head, and the top of the gravity, the top of the gravity in the head is inward. The direction is inward, but the tail is outward.
Where do you think the torque would be? Like, do you think it would be a torque like that forces it to go this way or this way?
This way. This way.
How
So we must consider the mass distribution of the arrow because it could influence the distance in the so it could turn in this surface.
Okay, so one thing I want to say, so first the arrow is pointed up vertically. So also if you want to talk about the torque like this, like the arrow is designed designed so that it won't like always tilt this way.
But actually
we move on to clarification questions from the reviewer.
Problem. My name is Jonas. I'll be reviewing this problem on behalf of the KTH team. So, first of all, let's look at the problem statement. I think this is the most important thing we're going to look at in this review. There's a lot of things. There's a very long problem statement. We can find a few things that we believe are very important here. So, the problem statement clearly says that we should take into account. We are professional architects who are able to take into account the effect of wind speed and the Coriolis effect and so on. So the problem statement clearly says tells us to disregard these parameters in the solution as an influence to the deviation of the arrow. The problem statement also asks how far the arrow will deviate as a result of factors that are beyond our control. So things that we can't take into consideration. And then it also asks how this answer is likely to change for a modern rifle and bullet. And we believe that the reporting team have not actually answered this question as it is stated in the problem statement. For the presentation, there were some delimitations made. This is good. This is very broad problem. They seemed reasonable. For the theory, there was a lot of theory about drag equation, height predictions for the flight of the arrow. There was some consideration of the Magnus effect and some turbulence, but there was also a lot of things that, like for instance, the Coriolis effect that was taken into consideration in the theory, which the problem statement we believe tells us not to. Also, most importantly, there were actually no conclusions made in this presentation. The reporter didn't actually make any numerical predictions of how far the arrow would deviate from its target. The opponent also missed all of these important things that the problem statement gives us. They did point out, however, a few things: the lack of optimization and some details of the experiments. There was the debate was mostly about torque of the arrow as it flies, which we think dragged on for a little too long. And so, for the discussion now, I would like to sort of start this over and start from the beginning and look at if we can actually make a model of the parameters that influence the deviation of the arrow. And we want to look at what parameters are, what of these parameters are out of our control, and how can we then set up a theory to test this. And from there we can take it in steps too long. So I would like to ask both of you, we can start with the reporter. We can start with the opponent, I think, would be more suitable. What parameters do you believe actually influence the deviation of the arrow as you shoot straight up? If you can take into consideration the Coriolis effect, wind speed, and so on.
Okay, actually, the important parameters including the deviation, of course, is the air gap caused by the wind, and the second is the Coriolis force. And the third, I think, is I just said the mass distribution.
Okay.
Yes.
But do any of you think there are any chaotic parameters here in play?
Yes, so as I mentioned, first I mentioned turbulence, which is clearly a chaotic effect. Second, I mentioned the transonic region deviation, which is also a very uncontrollable effect. As to, may I also address that you said that I should discount wind effect and Coriolis force. So first I did discount Coriolis force. I put the calculation in for arrow just for comparison about how big that number is compared to the effect of other effect. As you can see, I didn't really do Coriolis effect calculation for my bullet. So I put in that basically just for comparison, not really that I didn't discount it. Second, the effect of wind. Like I interpreted the effect of wind to be like how fast the wind actually pushes on the arrow, but the Magnus effect and the drag force are not directly they are indirectly related to the wind.
Okay, but so if I can just clarify a little bit what I'm talking about. There is, you have your bow and arrow like this, and you have your this is your arrow, and when you shoot the arrow with the bow, what will happen is that if you look at this from the side, you have the shaft, and then you have the string, and the arrow will actually want to go off to the side. Right? This is something called the Archer's paradox. And I'm wondering, have you taken this into consideration? And how would this phenomenon affect the trajectory the arrow takes?
So I did look up the Archer's what was that called? What Archer's problem, I guess. So it mostly happens with old bows, and with like the more modern kind of bows, that problem actually isn't a problem. It does go like in the direction of where you point it at. So at least during my experiments, I noticed that the arrow does shoot off like straight in the direction where I pointed at. So. Okay,
would you want to weigh in on this?
So I think I agree with her because actually we should use the arrows. Actually, the main parameters also should be considered the largest first. The logic is first, so we can change the arrows to control this parameters.
Okay, we're just about at the time for questions from the audience, so if there is a question, yes?
Yeah, I have a question, please.
We have a question up here.
So the problem statement says you use an Asian longbow. An Asian longbow doesn't have a centered mass. It has the arches paradox that it deflects on the side. And this creates oscillations. What do you think about that?
Oh, okay. So if you have to consider that, I think in that problem, so the arrow would shoot out and then it would bend a little bit, right, to correct it onto the correct trajectory. So I think that would slow down its speed, and you can imply like the effect from that. So basically the velocity.
Okay, now there's a lot of questions.
Thank you.
From you.
My question is very simply, could you let me see the picture of your PowerPoint? It's about like shot of it's like this. The figure.
I'm not actually sure if this is part of the discussion, so I think that you're supposed to remain seated. But if you want to add to place your question in words instead of
I want to ask this is your theoretical course or something else. Did you have any experiment data point on this figure or something else?
Where did I put it?
So we can show you.